3 slides, same start, same finish. A ball waiting at the top of each one, and when I let them go, there's nothing pushing them, just gravity. Watch which one wins. And it's not the straight one. The straight line is the shortest distance between those 2 points, and it still comes in last. The winner is that deep swooping curve, the one that actually dips below the finish line before it climbs back up to it. So, the longer path is the faster path. The ball that takes the detour beats the ball that goes direct. That feels wrong, and it bothered some of the cleverest people who ever lived for a very long time. So let's work out why it's true. If I ask you for the quickest way down, the straightest line is the natural answer. Shortest route, surely the fastest. But the problem is, you start out barely moving, and you stay slow for ages because gravity hasn't had time to pull you up to speed. So the next inquisitive decision is to try the opposite. You drop almost straight down at the start, and you get fast immediately, and then you tear across the bottom. But that doesn't win either. Yes, you've got all your speed now, but look at the long flat stretch you've left yourself, and flat ground doesn't make you any faster. Look at the tug of war there. Fall steeply and you gain speed early, but you add distance. Stay shallow and you keep it short, but you're sluggish when it counts. The best path has to be a compromise between those 2 poles. The only question is exactly which compromise. And that question turned out to be a deep one. This is an old puzzle. Galileo looked at it back in 1638, more than 50 years before anyone got it right, and he decided that the answer was the arc of a circle. Now, an arc of a circle really is better than a straight line, but it just isn't the winner. Galileo was also wrong. Gently, but he was wrong. Now, that should put you on alert. If the sharpest mind of his century can look straight at this and miss it, the real answer is hiding well. The answer finally came in 1696, and it came as a dare. A Swiss mathematician named Johann Bernoulli posed the problem in public and challenged the finest minds in the world to beat it, and he only gave them 6 months. Only a handful managed. Leibniz solved it, so did Bernoulli's own brother Jacob, and the 2 of them were bitter rivals, so this was one more thing to fight over. And then one solution turned up from England with no name attached. Bernoulli read the anonymous one and knew who had sent it. "I recognized a lion by his claw," he said. It was Newton, who, the story goes, came home from a long day running the Royal Mint and found the problem waiting in his post, and he solved it before morning. But here's the part that matters the most. To crack this, they had to invent a completely new kind of mathematics. Let me show you the wall that they hit, and the gorgeous way around it. Let's start with one solid fact though, because everything hangs upon it. When a ball rolls down a slope, its speed only depends on one thing: how far it has dropped. Not the route, just the height. Send the same ball down the same vertical distance along a gentle ramp or a steep one, and at the bottom it is moving at exactly the same speed. The path means nothing to the speedometer, only the fall does. So that is what we're really choosing when we shape a slide. At every height, the ball is locked to a certain speed, whether we like it or not. The only thing left in our hands is the shape of the route that carries it down through those heights. So let's just solve it head on. Add the time that the ball spends on every tiny piece of the journey, get the total, and then find the path that makes that total as small as possible. And you walk straight into a wall. Usually when you make something as small as possible, you're looking for a single best number. Here, you're looking for a best shape, choosing from infinitely many curves, all at the same time. In 1696, there was simply no tool for that, none at all. And that's not a footnote. This problem is the reason that tool got built in the first place. But Bernoulli didn't have it yet, so instead he did something much cleverer. He asked a sideways question: is there anything in nature that already finds the quickest path, all on its own with no mathematics at all? And there actually is. Picture a lifeguard. Someone's in trouble out in the sea, off down the beach at an angle. The lifeguard can sprint across dry sand, but swimming is slow and heavy going. What's the quickest way to reach them? It can't be a straight line. A straight line spends too long in the water where you have to crawl. So you do better and run a bit further along the sand first, so you enter the sea closer to them and spend less of the trip doing the slow part. The fastest route bends at the water's edge. It trims down the time you spend in the slow stuff, and no one's doing sums on the sand. This is what the quickest looks like when your speed changes partway through. Now hold that thought. What else moves slowly in some places, quickly in others, and always takes the quickest path? Light. Light always takes the route between 2 points that cost the least time, and when it crosses from something fast into something slow, like from air into glass, say, it bends for the very same reason the lifeguard bends their run. There's even an exact rule for how much it bends. The sine of an angle divided by the speed comes out the same on both sides. That's Snell's law, and every lens you've ever looked through depends on it. So here is Bernoulli's leap, and it is beautiful. Forget the ball for a moment. What if we treat the ball as a beam of light, hunting for the quickest way down? Picture the falling ball as light, sinking down through the world in flat layers. And in each layer it crosses, is allowed to travel a little faster than the last. Because that's exactly what falling does, it speeds you up. At every boundary between two layers, our beam refracts. It bends just slightly, the way light always bends when it gets quicker. Keep that single rule running. Sine of the angle over speed held steady the whole way down. Now make the layers thinner and thinner, infinitely many, each one infinitely thin, and the little staircase of bends melts into one smooth, clean curve. And because every single bend was the least time choice, the whole curve must be the least time path. We've actually found it by quietly turning gravity into light. And when you feed in that fact from earlier, that the speed grows like the square root of the drop, and follow the mass wherever it goes, the curve that falls out has a name you already know. It's a cycloid. Take an ordinary wheel, mark a single dot on its rim, and roll it along underneath a flat ceiling. That dot sweeps out an arch as the wheel turns. Now flip the arch upside down, and that is the fastest slide there is. The quickest way down was a shape we've been drawing with cartwheels the entire time. And the cycloid has one more secret, which is honestly just too much. Put several balls on the curve at different heights, some near the top, some close to the bottom, and let them all go at the same instant. They arrive at the bottom together, every single time. The ball that starts higher has further to travel, yes, but it also falls faster on the way, and on a cycloid, those two effects cancel out perfectly. The fastest descent curve is also the same arrival time curve. And that one wasn't just pretty. A Dutchman, Christian Huygens, worked out that a pendulum swinging along a cycloid keeps perfect time, no matter how wide or narrow the swing. He was chasing the great prize of his age. A clock steady enough to find your longitude out at sea so that ships would stop getting lost and breaking apart on coastlines. This humble rolling wheel curve sat right at the center of that. So essentially, a puzzle about a sliding ball pried open an entire branch of mathematics. The study of which shape, out of every shape there could be, makes some quantity as small as it can possibly get. And once you've seen it, you can't stop seeing it. For example, light takes the least time, a thrown ball follows the path of least action, planets and starlight trace the straightest possible lines through curved space, a soap film pulls itself tight into the smallest area it can find. The universe, it turns out, is just deeply and reliably lazy. It is forever reaching for the cheapest option on the menu. The brachistochrone is simply the first place where we caught it in the act and we learnt to write the rule down.